In this video, we are continuing our discussion of section 13.5. This is the chain rule with multi-variable functions. So we're going to expand the concept here. They look very similar there, but they're different. Excuse me. The number one says more intermediate values. Remember, intermediates are the ones that connect, like in this problem right below here. X, Y, and Z are intermediate values. So notice here, this is concept one. We're going to go over that. It says more intermediate. So we're going to deal with that first. Then in the second example here, we're going to deal with more independent. Remember, independent is the, that should say, I think, more independent. Yeah, so that's right. Okay, so we'll do that with the next one as well. Thought I had it wrong for a moment. I don't. Okay, so let's deal. First, we have this problem. I am going to make a mapping again. So I got x plus y plus z. And all those get related to t. I have three different pathways now to get to t. So the derivative here, this is the partial w with respect to x, and then dx dt. Then I have the partial w with respect to y, and then dy dt, and then partial w with respect to z, and then dz dt. This will give me my formula. So I'm going to write that dw dt is the partial of w with respect to x times dx dt plus the partial of w with respect to y times dy dt plus the partial of w with respect to z times dz dt. So there's my formula. I used the concept map there to come up with that. So now I just need each part, dw dx. All right, so dw dx in this case of that crazy function there, okay, x is inside of that, so we get 1, remember arctan, we get 1 plus 1 over the argument squared. It's very important that you get this down because it shows up in DE a lot. Times the derivative of the inside, which is xz with respect to x, I get az. So let me clear that up a little bit because it's written really bad. 1 plus x squared, z squared. All right, that's that partial. We also need dx dt. So dx, x was t, so we get 1. All right, so now we need the partial of w with respect to y. Oh, did we? Okay, so this didn't, we kind of blew past it, but that was part of it as well. But with respect to x, there's nothing there with x. There's nothing in the arctan with y, so that's a 0. And then we need the partial with z over y. So that's like 3 over y. If I did the derivative of that, I get negative 3 over y squared. So in this case, we're going to get a z, negative z over y squared. Right? Then we need also dy dt. I'm going to put them over here so they're kind of together. Y was t squared, so we get 2t. Back up there. Then we have one last dz with dw with respect to z. All right. The arctan has a z in it, so we get 1 over 1 plus x squared y squared, x squared z squared, x squared z squared, times the chain rule of xz, that gives me an x. So I get x over 1 plus x squared z squared. We also need dz dt. Z was sinh t, which I believe is cosine t. No negative for our hyperbolic cosines. You'll have a table if you don't know that. So now I just filled in dw dt equals, okay, so I got z over 1 plus x squared z squared. Then I have that times dx dt, that's a 1, plus negative z over y squared times 2t, plus, then that last one, x over 1 plus x squared z squared times cosh, right, or hyperbolic cosine of t. I'm going to leave it there. I mean, I could clean it up and do a common denominator, I guess, but it doesn't really get cleaner besides putting things in the numerators and stuff like that. I'm just going to go ahead and stop for the sake of time there. We're going to expand this now to the idea of number 2. This is more independent variables. So I want you to notice now we don't have an x, y, and z, but in each x and y we have a u and a v. So how we write this out, let's write this mapping out. I have w then it goes x to y, and then these have their own routes as well, u and v. So I have a path going here and then two more paths. Path going here and then two more paths. So I actually have a total of 4 possible paths here. So we have dw dx. Then we have, okay, and that's the partial because it's made up of x and y. This makes sense here too that I have to have partials because I have to choose. That one I have u on the top, or with respect to u. This one I'm going to have respect to v. Now the second branch is partial of w with respect to y. And then I have the partial of y with respect to u, and the partial of y with respect to v. I have to have both choices. So when we're figuring this out, and notice, maybe you noticed when we first started this problem, we have partial w's now of each one. I can't have the normal derivative of w with u because w essentially is made up of u and v's. We could always plug them in and find our partials that way if we wanted to, but I want to use the formula here. So dw, partial of w with respect to u, we'll do that one first. And we just follow the route of getting to our u's here. We have two different things that we're going to add together. So I have the partial of w with respect to x times, and then I go to the u one, partial of x with respect to u, plus the partial of w with respect to y. This is the other branch, so we went this way, and then this one goes here and then there. All right, we have two paths times the partial of y with respect to u. There are no v's in this one. If I wanted v's, I'd have the partial of w with respect to v, and I'd follow those paths. And you can kind of tell how this is going to work out here. Before, I never really used this map when I was in your spot. It does help. I just memorized it. It's not too bad, I don't think. You just have to respect your x's and y's and put them together. If you have multiple y's, z's, then you do that. If you have multiple u's and v's in the very end, then you would take multiple paths this way, and it would have to be completely all partials. All right, let's get a few examples using this. I like drawing the diagram. I think it helps. So we are going to do a little bit of that here. So notice I just changed x, y, and z. So let's write our diagram. They want partial of w with respect to u and partial of w with respect to v. So this goes out to an x, y, and a z. All right, and then each x, okay, x is made up of u. No v's there, so I'm not even going to write it. This y is made up of v, and then z is actually made up of u and v. So if I wanted the partial of w with respect to u, the first thing, okay, I follow the path. So this is w, partial of w with respect to x. This is partial w with respect to y. This is partial w with respect to z. And then each one of these, this is partial x with respect to u. This is partial y with respect to v. This is partial z with respect to u. And then this last one, partial z with respect to v. We get both on there. I don't do the u's and v's up there on the x and y because there isn't a route. I would get 0 if I take that route anyway. So I'm just going to use now. So partial of w with respect to x times partial of x with respect to u, plus, okay, partial of w with, well, there is no u on y, so I'm not going to do that. So I got dw now of z. I can skip the y times partial of z with respect to u. So I can figure that out that way. I'm going to do this one. We have the w's already, dw, so I'm just going to give them to you. Where did this go? Here we are. Okay, so in this case, we do have a, hold on one sec. I think I didn't change the problem. Change this in your notes if it's not changed already. This is going to be an x out front. So x tan, inverse tan yz. That's it. So we'll do that. All right, so I'm going to get each part. I guess I could do it up here. dw with dx. I need that. All right, that's just going to give me that arctan. There's an x inside. So I actually have a product rule. So I'm going to let the x be 1 first. Then I get xz. Then plus x times, and I got 1 over 1 plus x squared z squared. And then I'm going to get a 2x up top because of the chain rule. Okay, so I got inverse tan of xz plus, and we're going to get 2x squared over 1 plus x squared z squared. All that times, I need the x with respect to u, so that's 1/2, u to the negative 1/2, I'm just going to leave it. Plus, now I need the partial of w with respect to z. All right, this is going to, it's not a product rule this time, so I'm going to get an x squared over 1 plus x squared z squared. All right, give that a shot. If you can't see it, that's okay. If you can't, work it out. I got x squared over 1 plus x squared z squared times dz with respect to u. That is just a negative v sine u. So there is my expression. All right, dw now, dt, not tv. Okay, if I follow those paths up here, okay, x does not have a v, so I don't need to go that route, but I do have dw dy times the partial y with respect to v plus partial w with the partial z times partial z with respect to v. All right. Okay, the y, there is no y in my w, so I get a 0. Okay, so I got 0. It doesn't matter what this is, so I'm just going to do that. Plus dw dz, right? We already did that. That's right here. So we get x squared over 1 plus x squared z squared times, and then dz dv, that's just going to be a cosine of u. So there we go, both of those on the screen there. I'm just going to leave it like that because normally we would plug stuff in. On a test, I'm okay with you leaving it, stuff like that. Now, you moving forward, I would ask other professors because I know, like, the professor I steal most of his examples from, I know he states that he needs it simplified all the way down. I don't care at this point about the simplification part. All I care about is the calculus in between. So if you want to go all the way down, I know I have students that need to match the answer in the back of the book to feel good about it because that convinces them that they got it right. And I'm with you. I'm one of those students. Some of you are okay with just trusting your intuition. So whatever you prefer. Okay, I have one more for this video. We want to find the partial of w with respect to s, given all that. Now, we could write down this definition. Let's try. I want you to try to write it without the diagram. If you need the diagram, go ahead and pause, do that. So the partial of w with respect to s is the partial of x with, or partial of w, I already messed up, w with respect to x times the partial of x with respect to s plus dw with respect to y times the partial of y with respect to s plus the partial of w with respect to z times the partial of z with respect to s. All right, so we got to find all of these. The partial of w with partial x, right? We have that up there at top. Okay, I got 2xy, that's it. And then dx ds gets me a negative r sine s. dw dy, partial, right? I get x squared plus 2yz cubed. dy ds gets me r cosine s. And we got one more here, dw dz partial. Looking at w up there, the first one doesn't have a z, so it's 0. We get 3y squared z squared. And then dz ds, right? That one's not as clean. E to the x is e to the x. Oh, it is really clean. We just get r e to the s. Right? Then we're going to plug all that in. So we get dw, the partials though. Partial with respect to s is going to be 2xy times negative r sine s plus x squared plus 2yz cubed times r cosine of s plus 3y squared z squared times r e to the s. All right, we could plug things in too. Let's say that they wanted to know what is the partial of w when r equals 1 and s equals 0. Now, I'm not going to do this because it's just trig up there and some algebra. When this is true, we get x is 1, y is 0, and z is 1. We would write it just like this. We would plug all that in, x, y, z, r, and s. I'm going to leave this up to you to try to plug it in to match a 1. All right, that is our chain rules in 3 dimensions. We have 2 different types depending on how the independent is defined. If we have 1, meaning if we have 1 or 2 or 3 independent variables, that defines which derivative formula we want to use.